In this problem, we have a 8-kilogram ball and it's connected with a spring on the slope. Initially, the spring is compressed by 0.2 meter. And then under this applied force, 400 Newton force, which always maintains its direction, the spring is now stretched to 0.6 meter. And we need to determine the total work done to the ball during this process. The slope is smooth, which means that we do not need to consider friction. So let's consider how many forces are doing work in this case. We would have a weight force that does work, this applied force that does work, as well as a spring force that does work. Therefore, since this problem asks for the total work done to the ball during this process, we're going to determine the work done by these three individual forces and then add them together. So for the weight force, so we know that this equals to negative W times delta Y. We can actually determine the direction of the work manually. In this case, the ball has moved downwards. Therefore, weight force is doing positive work because the displacement is along the direction of the weight force. And the displacement is this much. And how much is this much? Well, we know that initially the spring is compressed by 0.2 meter. And now the spring is stretched to 0.6 meter. In other words, S1 equals to negative 0.2 meter, and then S2 equals to positive 0.6 meter. Therefore, delta S equals to S2 minus S1, which is positive 0.8 meter. So that's this distance right here. Therefore, for the weight force, the displacement is this vertical change, and that is 0.8 meter times sine 40 degree. Therefore, we have W, which is mg, the mass, times 9.81 meter per second squared, times the displacement, which is 0.8 meter times sine 40 degree. And that equals to 40.36 in the unit of joule, because all the quantities that we work with are given in their SI units. And then for the spring force, we know that the work done by the spring force between the two states, from state 1 to state 2, equals to negative 1/2 K, the spring constant, times S2 squared minus S1 squared. So we can just simply substitute the numbers in. So we have negative 1/2 times K, the spring constant is 300 Newton per meter, times S2 is 0.6 squared minus negative 0.2 squared. So from here we can determine that to be negative 48 in the unit of joule. And lastly, for the applied force, so for the applied force, because it is at an angle with the vertical direction, the angle is 15 degree. So it depends on how you want to do this. You can resolve the force into its x and y component and determine the work done by the x component and the y component respectively. We can try that first. The displacement is along the direction of the force. Therefore, it's the work is positive. So we have first the x component, and that is 400 Newton times, in this case, sine 15 degree, and the displacement is this much. So from here to here is 0.8 meter. So from here to here is 0.8 meter. Therefore, the displacement along the horizontal direction is this much, and that is 0.8 meter times cosine 40 degree. And then for the vertical component, this component right here, it has a magnitude of 400 times cosine 15 degree. The displacement is along the direction, vertical down. The displacement is this much, and that is going to be 0.8 times sine 40 degree. So we add these two contributions together, that equals to 262 joule. Or if you want to, because we can try an alternative approach, because this angle right here is 15 degree, this angle right here is 40 degree. Therefore, this angle right here is going to be 90 minus 40 minus 15, and that's 35 degree. Therefore, we have displacement from here to here of 0.8 meter, and we can resolve that along this direction and this direction. So instead of resolving the force, we resolve the displacement. So this component right here equals to S times cosine 35 degree. Therefore, we can instead calculate the work done by this force as its magnitude multiplied by the displacement along its direction, which is 0.8 meter times cosine 35 degree. And if you do the calculation, if you carry it out, you will find that it equals to 262 joule as well. So for the final answer, we're looking for the total work done to this ball during this process from state 1 to state 2. And that simply equals to the sum of all the work, therefore 40.36 joule minus 48 plus 262, and the answer is 254 joule. And that is the answer to this problem.